Welcome to the plenary session today. My name is Ilya Valov and I will chair this morning's session. It's my great pleasure to introduce our next plenary speaker, Professor Kazuya Terabe from National Institute of Material Science in Tsukuba in Japan. Professor Terabe, you know him maybe with his paper about atomic switch, which makes really a new quantity level and quality level in the research of MEMRISYS devices. And he continues his research further, not only on the atomic switch, but expanded to the world of nanoarchitectonics and nanoionic effects in MEMRISYS devices. And he will present now his overview summarizing his recent research on fusion of electronics and solid-state ionics by nanoarchitectonics. So, Professor Terabe, please.
Thank you very much, Ilya, for a very kind introduction. So, first of all, thank you so much, the committee and Professor Temis for giving that opportunity to introduce our research. So this shows outline of my talk. First, what is ionic nanoarchitectonics? Next is the various function devices created by ionic nanoarchitectonics. And then creating the atomic switch and its application, and finally creation of the neuromorphic device and its performance. So as you know, there is a three kinds of solid-state electrical conductors. One is the electric conductor. In this material, electron and the hole is moved, and which is a very high-speed transport and slight mass transport. This field is called the electric field. This behavior is treated in the physics, and the material is a metal, a semiconductor. So fabricated devices, IT device, and the solar cell, these are electronic information devices. So other material is ionic conductor. Ionic conductor in the material as an ion and the vacancies migrate. And this speed is very slow, and also large mass transport. This field called solid-state ionics, and this behavior is treated by the electrochemistry. So the used material is a solid electrolytes, namely ion conductor, or the device is mainly recently very focused on the battery and the fuel cell. This device is usually used in the environment energy devices. And the other is a mixed conductor. In this material, electron and ion is moved. So this field is also called the solid-state ionics field. Used material is a mixed conductor. So this material is used for the electrode of a fuel cell and the battery. This is also used in the environment energy devices. But in old days, so ionic devices used in electric information field. The pioneer developed by the Sanyo Electric Company in the 1970s. So they developed three kinds of the ionic devices for electric information field. One is the electrochemical potential memory. It's called memory odd. This is three terminal. This is two terminal. This electrode is made of the silver, and this is a mixed conductor, silver and electrode. This is a reference electrode, and between these electrode, electrolyte is insert like this. So, and this is two-terminal memory odd. This is a silver electrode, and this is silver and electron mixed conductor, and this is pure silver ion conductor. By applying the current, ions migrate in, and then into this mixed conductor. This behavior is very similar to the battery. So that according to the current, this is a Faraday current, the potential is increased between this electrode and this electrode. In these two electrodes, between this and this bias is increased. This is electromotive force, and this is actual devices, and this is time, and this is output voltage. Charge increase the voltage, and hold and discharge decrease like this. So that's it can use it can store amount of large charge flowing as a voltage change. This behavior is a battery. So and the other is electrochemical barrier resistors. This is three terminal devices. This is a lead wire, and this is silver, and this is a mixed conductor of the silver and electron mixed conductor. This is a silver solid ion silver conductor. So by applying voltage, current, ions migrate and insert into the mixed conductor. So mixed conductor is the resistance is changed by inserted the silver ion. This resistance is measured by these two electrodes. This is resistance change. This is charging and discharging and charging. So if silver ion is the concentration is a degree, resistance is increased and hold, and polarity is change. This is charge system, and silver ion is insert into the mixed conductor. Resistance is change. This behavior is nowadays synapse device is very similar to behavior. This is electrochemical switch. So this is very similar to this variable resistor, but lead wire is connected with mixed conductor at the point of contact. This point of contact is controlled by applying the voltage, applying the current. Silver is inserted into this material. This conductivity is increased, and point of contact is formed completely. But on the other hand, discharge, polarity is changed. This point of contact is disappeared. So using this behavior, they can operate the switching behavior. This is flow current. This is resistant, and this you can see the resistance increase quickly. This is the switching behavior. So this practical application of the memory ode is reported by this books. So this book is application of the solid electrolyte, and this published in the 1980. And also they are reported that this behavior, this paper title is a solid state ionics, the electrochemical analog memory cell with the solid electrolyte. So this is Sanyo electrode production. This is memory ode. This is memory ode. And the application is the ode tuning car radio and voltage integrator and pi helio integrator like this. But unfortunately, these ionic devices were phased out due to the development of more advanced semiconductor technology. So we are focusing the creation of the high-performance ionic device in the today's electronics information field. This technique is used in ionic nanoarchitectonics. So for fusing the electronics and ionics. So this shows ionic nanoarchitectonics fusing the electronics and solid-state ionics. As you know, this device structure is very simple. So this is very simple structures, and ionic conductor and ion and electronic conductor is sandwiched by electrode. So this is magnified image. So by applying the voltage and the preciously, we can control the atomic arrangement and the electrochemical phenomena as the interface, and which can be controlled by using the local transport of the small number of ions in the nanoscale and even atomic scale. So such a structural modulation can generate the interesting function such as neuromorphic properties. So what type of ion are viable? So up to now, there's so many various ion species moving in the solid or found. So for example, monovalent cation is lithium, sodium, potassium, silver, copper, proton. And this is alkyl metal ion. So the divalent cation is magnesium, strontium, and this is alkali earth metal. And the monovalent anion is fluoride, chloride, bromine, iodide, hydroxide. And also the divalent anion is oxygen ion. So this showed advanced in ionic conductivity, including the lithium, oxygen, fluoride, and proton, and hydride ion. So conductivity of various ions improved year by year thanks to the solid-state battery development. So this shows the best performance of in various ionic conduction with a solid. So lithium, sodium, magnesium, proton, and oxygen, the hydroxide. And this is ionic conductivity is here. These ionic conductivities are comparable to that of ionic aqueous solution, even at room temperature. So as you know, the all solid battery is required is a high ionic conductivity. This is essential. But neuromorphic device and other electric information devices, multifunctionality, stability, and the controllability of devices are very important. So that such a high ionic conductivity is not always necessary, but ion diversity may be necessary. So up to now, we created so many kind of the various devices, structures with different operating principle achieved by ionic nanoarchitectonics. This is a typical device structure. So first is we control the point of contact. This is very well known, the filament controls the devices. So, but we focus is the point of contact to the nanoscale and even atomic scale. And other is a control of a Schottky barrier. So you know that this is two-terminal devices. By applying voltage, we can control the Schottky barriers, and this can be used for the device operation. So this is also the control the electrode double layer. So this is three-terminal. So this is electrolyte. By applying voltage, ions migrate and form the electrode double layer like this. So we can control this channel, the conductivity. We can use this behavior to make the switching device or also the neuromorphic devices. And this is a control of the electrochemical reaction. So this is the same, but by applying voltage, ions migrate and generate the electrochemical reaction at the interface. So that then we can remove the surface atom is removed or adsorb, controlling the electrochemical reaction at the interface. So and also this is control the ion insertion by applying the voltage. Ion is inserted into such a functional material. We can control this. This is physical properties. And this is also the unique structure is so many electrodes. We can control the ion migrate. So it generates the electromotive force using such an electromotive force at each point. We can operate the device structure, device operation. So this shows creation of the various functional devices achieved by ionic nanoarchitectonics. This is a schematic diagram of the fabrication process. So this technique is based on the solid-state ionics and electronics and nanotechnology. Nanotechnology is very important, and used material is a solid electrolyte and ion electron mixed conductor. Techniques is the control of local ion transfer and the control of local electrochemical reaction. So using these techniques, we control the interface reconstruction and composition. And using electron double layer, the carrier doping, ion adsorption, and ion insertion, and lattice distortion, and other effects. So using these techniques, we can generate a new functionality and improve the performance, such as electrochemical property and the magnetic properties, optical properties, high temperature superconducting properties. So these shows we created so many AI and IT devices, such as decision-making devices, artificial synapse devices, physical reservoir devices, artificial sensory devices, and the barrier capacitor, and atomic switch, multi-level memory, and the variable resistance devices, barrier magnetic devices, barrier superconducting device, and so on. So in this presentation, the mainly focus is the artificial synapse device, the physical reservoir, and artificial sensory devices, and atomic switch, multi-level memory. So at first is let me introduce is atomic switch through the point of contact at the atomic scale. This is a two-terminal devices. This is a conductive filament, so we can control the point of contact atomic scale. This is a three-terminal atomic switch. This is a point of contact, and this is a gate and the source drain. We can control the gate bias. Point of contact can be controlled the atomic scale. So first, we confirm the atomic scale point of contact using scanning tunnel microscopy. This is a STM system. So this is a silver cyanide crystal tip, and this is tip. This is STM system. And by applying voltage, we keep the tunnel gap. And if applied voltage, tunnel current is a flow. So this is correspond to the resistance. So at first is here, this corresponds to the tunnel resistance. So under applied voltage, so silver is precipitate at the atomic scale. This distance is about 1 nanometer. So using the tunnel current, electrochemical reaction occurs, and the silver atom is precipitate. So this shows is IP resistance change. So by applying the negative voltage, so silver atom is precipitate, and the contact is platinum electrode and at atomic scale, resistance degree quickly, like this. And then polarities change. Redox reaction is occurred, and silver atom is dissolved into the silver mixed conductor, ion mixed conductor, and this is behavior is according to like this, and go back and first position. So that we confirm the such an atomic scale point of contact can be controlled. So using the STM, next step we are fabricate the actual device structure. So this shows fabrication of the atomic switch devices using the conventional semiconductor process. So we have to control the point of contact atomic scale. So we fabricate gap type atomic switch using the electron tunnel. This is the same as the STM experiment. This is also gapless atomic switch using the nanostructure. This is a very small nanostructure area that by applying voltage, silver ion is migrated and precipitated. In this case, is using the tunnel current. And in this case, it's also the fabricated such a nanofilament like this. So we control the point of contact atomic scale. This is a conductance change. So this is quantum conductance is observed such a stepwise resistance change. And the polarity is change. Resistance is degrees. Resistance is degree. Conductance is degree like this. So this is correspond to the quantum conductance, which is point of contact is formed as the atomic scale. So this is also the gapless type atomic switch. Conductance changes like this. You can see the quantum conductance observed and the polarity change. Point of contact is degrees like this. Quantum conductance states is degrees like this. And this is contact is disappeared here. So this shows a quantum conductance characteristic gapless atomic switch based on the silver filament. So this is a nanoscale filament shows such a quantum conductance like this. So we examine the stability of the quantum conductance. So this is a quantum conductance state 2G, 3G, 4G, 5G, 7G, 9G. This is time, this is second. You can see that each quantum conductance state is stable a few seconds. So this is a quantum conductance scale state histogram by counting the steps many times quantum conductance observed, and this is counting the step. So you can see the most predominant is integer multiples like this. But half integer multiple is also observed. So that we examine the stability of the point of contact of the different number of the silver atom by a first principle density functional theory simulation. This is model. So this is 10 silver atom is forms such a point of contact. So and this is 11 silver atom is forms such a point of contact, and this is 12 silver atom is such a contact. This is a result. So 10 atoms, this one is very stable around the 1G state. So that which corresponds to the integer multiple one state. This is very stable here. And but 11 and 12 atom point of contact structure is such a between the 1 or 2 or 3 is stable like this. So that this means these simulations reveals that controlling the quantum conductance state is not so easy. So, but we try to fabricate the quantum conductance using the conventional semiconductor techniques. This is 2 platinum wire. This is a silver wire. Cross point, we fabricate the atomic switch. This is a fabrication procedure. So at first is a fabrication of the silver wire and the sacralization. The silver wire is partially like this. And we fabricate the silver sulfide mixed conductor and deposition the silver again and covered by platinum wire. And if applied voltage, this silver wire is dissolved into the silver sulfur layer so that we can create the tunnel gap and we can operate the switching behavior. Using such a structure, we control the quantum conductance of each atom switch. So this is, in this case, is a 2 atomic switch, and independently from the quantum conductance states 0 to 3. So you can see that this is 1, 2, 3 quantum conductance is controlled. This is the second and 1 or 2 second stable. And this is number 2 atomic switch is also, we can control 1, 2, 3, 1, 2, 3, 1, 2, 3. So that totally we can control the 4 state and also the 4 state, totally 60 state is controlled independent. And this is used for the multi-state memory. So we try to development of the practical application of the atomic switch together with a Japanese electronic company. So for practical use of a gapless atomic switch. So we invented the atomic switches around 2000 and published the paper and then collaborate with the creation of the integrated circuit like this. And finally, NEC company is a success to the development of FPGA with atomic switch. This is where this is atomic structure in the devices. This is a FPGA chip. So this atomic switch, the comparison is a conventional semiconductor switch. Atomic switch is the size is reduced to 1/30, and the power consumption is 1/10, and non-volatile, and simple structure and low manufacturing cost, and the switching speed is comparable to nanosecond. Furthermore, we found excellent resistance in the harsh environment, such as electromagnetic noise, temperature change. So usually is 4 Kelvin to the 423 Kelvin. And the radiation and the cosmic ray, a very excellent resistance. So, and radiation is error occurrence is less than 100 compared to the conventional semiconductor. So that's its application extended the AI and the IoT field, such as a robot and the satellite system. Such advantages are made from the metal filament operation. So this is an advanced FPGA circuit with atomic switches. This is a conventional FPGA. So this is a logic cell. Each logic cell is connected by lead wire, and each point is a conventional FPGA. The semiconductor switch is placed at each point. But this switch is very large. So replaced with atomic switch, this size is very small and has a very simple structure. and so that NEC company can reduce this chip size, and it's a very low power consumption because of the lead wire distance is very small. And if same size of the conventional FPGA, so more logic cell can be introduced like this, so that about the 10,000 times function are realized by the controlling the fine logic cell. So, and this shows the performance of the evaluation of the FPGA with the atomic switch in a space radiation environment by NEC, and JAXA is a Japanese Space Institute. So this is FPGA with atomic switch chip. And this chip is equipped with a video module. And this is loaded into such a satellite system and launched by the JAXA. And the demonstrate is 1 year. So this is a satellite, and this is actual monitor camera image. This is sun, this is Earth. So they confirm to work property for 1 year. And zero radiation error, excellent radiation tolerance. So this is also used the atomic switch based FPGA in a high temperature environment using the humanoid robot. This is NEC and Tokyo University collaboration research. So this is a humanoid robot. Usually they operate by using the MOSFET based FPGA. So replacing to this FPGA to increase high temperature durability. So this is atomic switch based FPGA. This shows the atomic switch performance and temperature changing. So this is temperature, and this is on resistance. So MOSFET resistance is changed like this, but atomic switch is very stable. So, and also this is off current. So this is temperature. Even changing the temperature, atomic switch of current is very stable, but MOSFET is very changed rapidly, a very large amount of the change like this. So this is temperature, and this is active power. So this is a MOSFET-based FPGA. Active power increases with increasing the temperature like this, but atomic switches based FPGA is very stable. So it shows it reveals the active power of atomic switch-based FPGA is 80% less than that of MOSFET-based FPGA, resulting from the smaller leakage of power. So this is also examined in the very low temperature. This is a cryogenic operation of atomic switch at 4 Kelvin for controlling the superconductor qubit. This is NanoBridge system company. So this is atomic switch, gapless atomic switch. This is ruthenium electrode, and this is copper electrode, and this is polymer solid electrodes. This thickness is very thin, and around the 10 nanometer. So this is this gapless atomic switch is fabricated by using the semiconductor process. So this shows switching behavior at room temperature and 4 Kelvin. So this is a log scale, and this is linear scale. You can see the switching behavior is at room temperature, but 4 Kelvin is also observed like this. So this switching voltage is not so different, 2 volt and 2.5 voltage. So this is shows the temperature of the switching voltage relation. So 400 Kelvin, the switching voltage is about 1.8 volt, but the decreased temperature and about 4 Kelvin, so switching voltage is 2.5 voltage, not so different. And also this is on and off resistance change during the temperature is changing, during the temperature changing. This is 400 Kelvin, and this is 4 Kelvin. So on resistance is almost same. And also the off resistance is a little change, but not so much. So that it shows atomic switch is very suitable for the low temperature switching devices. So this is applied to the quantum chip control. This is a conventional quantum computing system using the CMOS-based FPGA. This is the quantum chip is very low, located at a very low temperature, and the FPGA is about room temperature. This distance is a very long wire, so that it generates the noise and something. But compared to the this one, so this is replacing with atomic switch FPGA, so it can put in use in the 4 Kelvin condition. So this lead wire is very short distance. It is a very performance is improved, so that future high performance quantum computing system using the atomic switch based system. So let's move to the next topics. So we try to the IONIC device is for application of the hardware-oriented AI system. It is brain-inspired computing. So this is well-known figure. So this is year, and this is computational performance. So it recently increased. So recently doubling every 2 months for the required training the computational performance. So which shows rapidly increased power consumption. So that this is because this system is a conventional type, and the configuration is a software and a CMOS computer. So the operating principle is calculation processing and based on the enormous software and data. So expected advanced type is a brain type computer, you know very well. So that is a neuromorphic chip and judge itself like a human brain. So this is a conventional type is generally speaking the software learning, high power consumption. But a brain type computer is a material learning using the neuromorphic device such as ionic devices, low power consumption. So that we are focusing developing the neuromorphic devices using the ionic devices. So this shows ionic device fabrication for the neural network or brain-inspired computing. So you know that typically there are two kinds of the neural network. One is a hierarchy artificial neural network like this. This is realized by crossbar structures with the synapse device. This synapse devices can be fabricated using the ionic devices. So required the synapse devices characteristics, linear and symmetrical analog resistance change, and static stability like this. And the other is a recurrent neural network model. This neural network is a precious information processing and relatively high power consumption. And on the other hand, recurrent neural network model, this is a reservoir network. This is very rapid and approximate information processing and relatively low power consumption. Such a reservoir system can be realized by reservoir devices using the ionic devices worked by the electrochemical phenomena. So required reservoir device characteristic is in response to the input signal, high dimensionality and the non-linearity, the short-term memory, and the dynamic adaptability. So synapse device is realized through the point of contact or control of the atomic switch. So you can see the point of contact in the atomic scale is like this. Using such behavior, we can control the synapse behavior, so which is plasticity. So that is a plasticity change, resistance change. So we fabricate the synapse and the dendrite function realized by various atomic switch structures. So one is a nanowire structure. This is fabricated by Professor Jim Jemski. So, and also this is a nanoparticle. This is a mixed conductor silver sulfide nanoparticle. So the size is about 20 nanometers. So such a nanoparticle is covered by molecular layer, and this forms the atomic switch. So this is also the this is nanoparticle. By controlling the applied voltage, silver filament composed of the numerous interconnect nanoparticle like this. Using these techniques, we can fabricate such a filament like this. This can be used as a dendritic function. So next is we use the electro double layer transistor to create the neuromorphic devices such as the reservoir and the synapse devices. This is the electro double layer devices, source and drain and the gate. This is a solid electrolyte. By applying voltage, we can form the electro double layer. So this is an image of the electro double layer transistor. By applying voltage, so ion migrate and electro double layer forms, and electron charge carrier is formed like this, so that it is easily to current flow, and voltage change, such a electro double layer disappeared. So at first, Tsuchiya is fabricated such a electro double layer transistor using the oxygen ion conductor. This is applied voltage, oxygen vacancy migrated and generated the electro double layer. This is the drain source current, and this is gate bias. You can see that such a resistance change can be observed. So this is very interesting, how fast we can switch. So this is, we try to, Tsuchiya and Takayanagi try to the fastest switching devices using the proton conductor and also proton terminated diamond layer. Proton is very small, so that ions migration speed is very fast. So that using such devices, switching behavior is examined. Like this is gate bias. This is drain current change. So using this area, they can estimate the switching speed. So that this is about 10 to minus 5 second speed. This switching speed is comparison with other transistors with similar operating principle. This is fastest in the world. So we also examine the ion electron behavior at the electrical double layer. So by finite element simulation. So this shows we investigate the use of the physical simulation to analyze, examine the lithium-ion distribution and the Hall distribution. This is a model. This is electrolyte, and this is channel, and correspond to the interface here. And this is lithium concentration, and this is a Hall density. This is a Hall density in a channel. So this is simulation. The thickness of the electron double layer is about 0.3 nanometer. This is also examining the potential distribution of the electronic double layer estimated from the hard X-ray electron spectroscopy. You can see that there is a big rapid change potential like this. This corresponds to the electron double layer. This thickness is also the 0.3 nanometer, so that this simulation and experimental data is almost constant with each other. So this is a simulation of ion and electron dynamics at the electron double layer under the application of the voltage. This is a model. This is electrolyte. This is a channel. This is the input bias, and this is drain current. Under this condition, this shows distribution lithium ion and the Hall density at the interface. This is a simulation. This is input bias. So drain current increase. You can see the Hall density, lithium density, and the Hall density is changed like this. Very complicated behavior. Like this. So such a property is required for reservoir devices such as the nonlinearity and the short-term memory and the high dimensionality are generated by such a complex ion-electron dynamics. So we fabricate a reservoir device based on the electron double layer transistor. This is a structure of the electron double layer transistor. This is a lithium conductor. Lithium conductor is a lithium silicon zirconium oxide amorphous layer, and this is a diamond terminated by proton. So this is this is drain current. This is gate bias. This is time. So input the gate bias like this. Drain current is a decrease and increase like this. But this is asymmetric relaxation. This is analogical, namely the nonlinearity and the short-term memory is observed. So such a reservoir device can be created using the nonlinearity and the short-term memory properties. So this shows the performance of the reservoir device based on the electron double layer transistor. This is sample data. We put the reservoir bias devices. So 4 pixel gate bias pulse to stream. So this is readout network. And by testing, weight value is decided. And this is performance. So recombination accuracy is about 89%. So this is so-so performance. So and this is reservoir devices with a multi-channel for even better performance. So this is a simple serial deep structure using the 2 electron double layer transistor with multi-output channel. This you can see that this is output multi-channel. So increasing the dimensionality of the output data. This is a series reservoir system. So this shows a prediction error. So performance is improved by such a series deep structure. So this is improved by such a structure. So fabrication of the reservoir device and the sensor system for advanced edge computing. So this is an image of the edge computing. So there is so many events. The sensor is collecting such data from this event. And usually this data is directly transferred to the supercomputer. But a supercomputer is a very, so many data so that it's very high power consumption. But instead of such a system, the reservoir device is put here, and the sensor data is processed using the reservoir device and the learning and the inference, and transfer the necessary data to the cloud. So that using such a system, reduction of the size of the power consumption and the reduction of the information security issue and so on. So recently the reservoir device performance is improved so much, so that this shows prediction error, it means the performance, and this is a computational load. So this is a deep learning and system, very high prediction error, low prediction error, high performance, but computational load is very high. But compared to such a deep learning, reservoir computing is same equivalent performance, is computational load is very small. So that is very suitable for such a edge computing system. So this is a speech recognition system using the electret variation and the sensor and reservoir devices. So this is electret vibration center. This is output data. For example, voice is 0, 1, 2, 3, 4. Like this, we can obtain the different voltage signal. So input signal, signal voltage, reservoir devices, and output like so many high-dimensional data and classification. So this is a very easy system, and it is possible to direct classification without machine learning. So this is actually the reservoir devices. This is source and drain, and many kind of the structure and the size, drain, electrode. And we can obtain the 6 kind of the voltage output. So that this is very kind of the output, different output signal. So using such a output signal, so this shows the performance of the performance is a recognition of the speech, digital speech. So this is a recognition accuracy is 80%. We also fabricate gas recognition system using the gas sensor and the reservoir devices. This is a membrane type surface stress sensor. This is and this membrane is direct stress is a direct stress caused by gas adsorption like this. So detected by this section. And if change the membrane, this output voltage is changed. In this case, 3 kind of the membrane material. So this is aldehyde and alcohol and acid gas. So we can obtain many kind of the output. So this is output signal, and only use this area like this. So this data is input to the reservoir devices like this, and this is output signal. So accuracy is about almost 100%. It is very good accuracy, and also the processing speed is very high because of only very simple structure, simple device system. Okay, next is also the ion insertion created neuromorphic devices such as the reservoir device. So this is electrochemical, this is lithium conductor, this is magnetite. If applied voltage, lithium is inserted magnetite. So according to the lithium insertion into the magnetite, such electrochemical reaction is occurred. And so that we can control the up and down spin number. So before the lithium insertion, total spin number is 2 up. And also the lithium inserted into this, according to the lithium insertion content, shows that this up spin number is shows like this. So that it means up spin decreased by lithium doping. So which means magnetic can be controlled by lithium doping. This is also electronic structure of a near Fermi energy. So this is magnetite, lithium doped magnetite. So you can see the downspin is generated. So it means carrier density is increased by lithium doping. So that it means electrochemical conductivity change by lithium doping. So this shows magnetism change by applying voltage. So at first is before the applied voltage, ferromagnetic property like this. And by applying voltage, lithium is inserted like this, change to the magnetization property. It is almost a paramagnetic behavior. So like this. And this is also the electric conductivity. So this is carrier density, and this is conductance. By applying gate voltage, conductivity is increase, and also the carrier density increase. So using this devices, we try to fabricate the electrode reservoir devices. This is a sample signal like this, and this is a reservoir device, lithium conductor, and this is magnetite. This is output electrode. For output electrode is fabricated, and this is between this electrode, voltage is obtained, which is derived from the magnetic resistance. And also this and this one, this electrode, between this electrode, we can obtain the voltage change. This is derived from the magnetism, which is also related to the Hall effect. This is output signal like this. So this is prediction performance of the blood glucose level. So this is measured blood glucose level. The data is changed to the pulse voltage like this, and the input here. And we examine the performance of the blood glucose level prediction. This is training area. This is a test. You can see that this is actual measured data, and this is reservoir data. This data is very coincident with each other. So predicted data is using the reservoir device is a good agreement with the actual measured data. So finally, we also fabricate artificial visual ionic devices mimicking the human optical illusion using the ion insertion. So this shows the retina of a human eye. So photoreceptor is receive the light signal and convert to the electric signal. And the next layer, bipolar neuron is receive the electric signal directly and or indirectly through the horizontal cell like this. So this such a human eye structure is generated optical illusion function. This is very well known, the Mach band wave effect. So border between the light and dark is here is appear to be emphasized. This is a human illusion. We try to make mimic such a retina structure using the ionic devices which operate by the ion insertion in the lithium cobalt oxide. This is a channel, so many channels. This is lithium cobalt oxide. This is lithium and electron mixed conductor. Here is LiPo. LiPo is a pure lithium ion conductor. So if we input the voltage according to the image, such a contrast here, so there is some voltage gap, so that ion is migrate around here, which here, and current is changed like around here. So that using these techniques, we can control we can mimic such a Maha band effect. So this is an array of the artificial visual ionic devices like this. This is many array. This is simulation, and this is input image, and input density is the voltage according to the contrast like this. This is input image. So this is output image. This is current. This shows the image is the output image. You can see the light and dark boundary of the input image can be clearly extracted like this using such a artificial visual ionic devices. This ability of a human eye to perceive the boundary between the light and dark with emphasis can mimic by ionic device array without the complex software and the electronic circuit. So this is shows the prospect of the solid-state ionic devices. Actually, focusing on the application is artificial intelligence technology. So solid-state ionics has a very variety of the devices, such as the battery, actuator, memory, and artificial perception, the artificial intelligence, display, and the sensor. Using such a device, we expect the autonomous robot utilizing the various solid-state ionic devices. This is a human brain, and this is artificial sensor, and this is a battery, and this is a actuator, something. So we expect such an application. So conclusion that the ionic nanoarchitectonics make it possible to create a new concept of the ionic device with various function and performance. Ionic devices creation using the method is expected to be a promising the candidate for enhancing the electronics and AI technology. They are collaborator, Aono and Hasera, something. So thank you so much. Thank you for your kind attention.